Okay, let's get started. Now, I'm assuming that A, you went to recitation yesterday. B, that even if you didn't, you know how to separate variables and you know how to construct simple models of solve physical problems with differential equations and possibly even solve them. So you should have learned that either in high school or 1801 here, or yeah. So I'm going to start from that point. Assume you know that. I'm not going to tell you what differential equations are or what modeling is. If you still are uncertain about those things, the book has a very long and good explanation of it, and just read that stuff. So we're talking about first order ODEs. ODE, I'll only use two acronyms. ODE is ordinary differential equations. I think all of MIT knows that, whether they've been taking it course or not. So we're talking about first order ODEs. Which in standard form are written, you isolate the derivative of y with respect to x, let's say, on the left-hand side, and on the right-hand side, you write everything else. You can't always do this very well, but for today, I'm going to assume that it has been done and it's doable. So, for example, some of the ones that will be considered either today or in the problem set are things like, y prime equals x over y. That's pretty simple. The problem set has y prime equals, let's see, x minus y squared. And it also has y prime equals y minus x squared. There are others too. Now, when you look at this, of course, you can solve by separating variables. So this is solvable. This one is, in neither of these can you separate variables, and they look extremely similar, but they are extremely dissimilar. The most dissimilar about them is that this one is easily solvable, and you'll learn, if you don't know already, next Friday, how to solve this one. This one, which looks almost the same, is unsolvable in a certain sense. Namely, there are no elementary functions which you can write down which will give a solution of that differential equation. So right away one confronts the most significant fact that even for the simplest possible differential equations, those which only involve the first derivative, it's possible to write down extremely looking simple guys. I'll put this one up in blue to indicate that it's bad. Whoops, sorry. I mean, not really bad, but recalcitrant. It's not solvable in the ordinary sense in which you think of an equation as solvable. And since those equations are the rule rather than the exception, I'm going to devote this first day to not solving a single differential equation, but indicating to you what you do when you meet a blue equation like that. What do you do with it? So this first day is going to be devoted to geometric ways of looking at differential equations and numerical. At the very end, I'll talk a little bit about numerical ways, and you'll work on both of those for the first problem set. So what's our geometric view of differential equations? Well, it's something that's contrasted with the usual procedures by which you solve things, and find elementary functions which solve them. I'll call that the analytic method. So on the one hand, we have the analytic ideas in which you write down explicitly the equation y prime equals f of x y, And you look for certain functions which are called its solutions. Now, so there's the ODE. And y1 of x, notice I don't use a separate letter. I don't use G or H or something like that for the solution because the letters multiply so quickly, that is, like rabbits, multiply in the sense of rabbits, that after a while, if you keep using different letters for each new idea, you can't figure out what you're talking about. So I'll use y1 means it's a solution of this differential equation. Of course, the differential equation has many solutions containing an arbitrary constant. So we'll call this a solution. Now, the geometric view guy that corresponds to this version of writing the equation is something called a direction field. And the solution is, from the geometric point of view, something called an integral curve. So let me explain, if you don't know, what the direction field is. I know for some of you I'm reviewing what you learned in high school. Those of you who had the BC syllabus in high school should know these things, but it never hurts to get a little more practice. And in any event, I think the computer stuff that you'll be doing on the problem set, a certain amount of it should be novel to you. It was novel to me, so why not to you? So what's a direction field? Well, a direction field is you take the plane, and at each point of the plane, of course that's an impossibility, but you pick some points of the plane, you draw what's called a little line element. So there's a point, it's a little line, and the only thing which distinguishes it outside of its position in the plane, so here's the point xy at which we're drawing this line element, is its slope. And what is its slope? Its slope is to be f of xy. And now you fill up the plane with these things until you're tired of putting them in. So I'm going to get tired pretty quickly, so I don't know. Let's not make them all go the same way. That sort of seems cheating. Here, how about, there's a few randomly chosen line elements that I put in, and I put in the slopes at random since I didn't have any particular differential equation in mind. Now, the integral curve, so those are the line elements, and the integral curve is a curve which goes through the plane and at every point is tangent to the line element there.